So let's take a look at Dr. C number 1 from homework 12. This is the problem where you're at the orbiting International Space Station and you're watching a couple of friends who are floating outside. You've got Anne and you've got Sam and you've got a hula hoop. And so Anne is going to throw the hula hoop. Both are initially at rest from your point of view, from your origin. And Anne is holding a hula hoop, which she's going to throw up to Sam at the same time she gives it a spin. And so you're told that you are able to measure the angular speed and the translational speed, let's call the hula hoop HH, of the hula hoop while it's moving between them. And although I'm drawing this as omega, that's an angular speed, remember that what you're actually given is the frequency, conventional frequency of the hula hoop when you observe it is 2.5 revolutions per second, or revolutions has no dimensions. And you can convert back and forth between omega and f because omega is 2 pi f, 2 pi radians per revolution times revolutions per second. Okay. Now, because they're in space, in empty space, there's no net force acting between them. So the net force is 0, and there's no net torque acting on this system. Okay, and so when you know the sums of the forces, or the net force is 0, you know translation momentum is conserved. And if there's no net torque acting on the system, angular momentum, L, is conserved. And so those are the principles we'll use to answer the question, what's the motion of Anne and what's the motion of Sam look like after Anne throws a hula hoop and Sam catches it? Because if Anne gives some upward momentum to the hula hoop, then she has to gain an equal amount of momentum away from the hula hoop. And the same thing if she gives it a spin in some sense, and note that with omega pointing up, that the sense of the rotation would be this, and although the direction of the omega vector is upward. Okay, so that means that she'll have to gain an opposite sense of rotation with a downward omega vector for Anne. So let's analyze this motion in 2 steps. Forget Sam for a moment and just say what happens to Anne after she throws the hula hoop. Because Sam's catching it won't change what happens to her. Okay, so what we're going to do is use the principle that the momentum is conserved. So the momentum of the Anne hula hoop system before she throws it equals the momentum afterwards. Well, the momentum afterwards is the momentum of Anne, okay, plus the momentum of the hula hoop. Okay, that's the final momentum after she tosses it, or before Sam catches it. Okay, and that has to be equal to translational momentum before she throws it, but they're just standing there at rest in space from your frame of reference. So that initial translational momentum is 0, which tells us that the momentum of Anne after she tosses it is just negative the momentum of the hula hoop. And now putting that in terms, things were given and after, the mass of Anne, the velocity of Anne after she throws the hula hoop equals negative the mass of the hula hoop, the velocity of the hula hoop. Now when you observe it, okay, and just solving for the velocity of Anne, that's just equal to negative the mass of the hula hoop divided by the mass of Anne, the velocity of the hula hoop. Plug in the values. I won't put in the dimensions of each of these, but -2 is the mass, kilograms is the mass of the hula hoop, 65 kilograms is the mass of Anne, so kilograms cancels out, and 3.9 meters per second is the velocity that you observe for the hula hoop while it's moving between Anne and Sam. And so this just comes out to -0.12 meters per second. Now I didn't actually draw a coordinate system here. I probably should have said plus y is up. But all this negative sign tells you is that she's moving away from the direction of the hula hoop, that the hula hoop is moving. Okay, so that's Anne's translational velocity. Now her angular velocity can be found from the principle of conservation of angular momentum. L of Anne plus L of the hula hoop at the point where the hula hoop is observed between them, okay, has to be equal to the initial angular momentum of the AN hula hoop system. Well, she's just at rest there in space, as is the hula hoop, so this is 0. So this tells us that the final angular momentum of AN is just the negative of the angular momentum of the hula hoop when you observe it after she throws it. And writing out angular momentum in terms of omegas, etc., that's just IA omega A for AN equals negative I the hula hoop, omega of the hula hoop. Okay. And we can solve this for the angular frequency of the AN, just negative moment of inertia of the hula hoop, divided by the moment of inertia of AN, which you're given, divided omega of the hula hoop. Now you want to be a little bit careful. You're given the rotational motion of the hula hoop in terms of revolutions per second, and angular momentum is written in terms of omega and angular velocity, but we convert back and forth by dividing both sides by 2 pi radians per revolution. And so this equation then becomes the frequency of AN equals negative I of the hula hoop, moment of inertia of the hula hoop, over the moment of inertia of AN, divided by, or times the frequency of the hula hoop. Okay, so the frequency of AN, after everything is said and done, well, we need the moment of inertia of the hula hoop, but it's a hoop, which means its moment of inertia is just given by m, its mass times its radius squared, same moment of inertia as a point particle would have at the same distance. We've worked that out in class, divided by the moment of inertia of an AN, which is a number you're given, and the frequency of the hula hoop, which you're also given. So this is equal to, let's write that equal to, we'll plug in the numbers, 2.0 for the mass of the hula hoop, 0.51 squared for the radius of the hula hoop squared. These are actual real numbers. I looked them up on Google for the size of a hula hoop, divided by 0.55 for the moment of inertia, again with appropriate units, for the moment of inertia of AN, times the frequency that you watch, you observe out the window of the space station. And I shouldn't neglect the negative sign here. I have up here, negative, negative. So this is negative 2.4, and it's revolutions per second. I'll just write that as inverse seconds. You can write the revolutions if you want to be clear, so no one confuses it with radians per second, since both are dimensionless. The negative sign here just means that if this is what you're considering the positive sense for the rotation of the hula hoop, and will be rotating in the opposite direction, or opposite sense. So we're halfway done with this problem. Now we just have to forget about Anne. We know what she's doing. What happens to Sam, who's initially at rest in space, but he's got this rotating, translating hula hoop coming. He's going to catch it. But again, the momentum of the hula hoop Sam system doesn't change, angular or translational momentum. So this was all for Anne. Now let's switch to Sam and see what happens to him. But we use exactly the same concepts. P naught equals P final. The initial momentum of the Sam hula hoop system is all, translational momentum is all in the hula hoop. Okay, but after he catches it, the momentum, translational momentum, is the combined Sam plus hula hoop system. Okay, and so writing that out in terms of quantities that we can appreciate, that would just be the mass of the hula hoop times the velocity of the hula hoop, which you're given, and while it's traveling between the two of them, has to be equal to the mass of Sam plus the mass of the hula hoop, because they're now combined. It's like a completely inelastic collision. The velocity of Sam plus the hula hoop. One velocity for both because they're combined. So we can solve for that velocity. Velocity of Sam plus the hula hoop, which is the velocity of Sam that we're asked for, is just equal to the mass of the hula hoop. Just this divided by that term. Mass of Sam plus mass of hula hoop times the velocity of the hula hoop in transit between them. Plug in the values. The mass of the hula hoop again is 2.0 kilograms. The mass of the combined Sam hula hoop system is 92 kilograms. And the velocity of the hula hoop was 3.9 meters per second. So 0.085 meters per second. And we're almost done. Now we just have to figure out, well, what's Sam's angular motion look like? okay, after he catches the hula hoop. And again, we'll just use this idea that the original momentum, which is all in the hula hoop as it's flying towards him, equals the final momentum when Sam catches the hula hoop. Okay, and that becomes the angular momentum of the hula hoop equals the angular momentum of the hula hoop plus Sam's system. Okay. And we write that out as I hula hoop omega hula hoop, that's the initial angular momentum, equals, now we have the combined moment of inertia for the two of them, so that's I Sam plus I hula hoop omega, and I'll just write it as Sam because it's the hula hoop and Sam will have the same angular velocity, okay, after he catches it and holds on to it. So solving for omega Sam, just rearrange this equation. It's I hula hoop divided by I Sam plus I hula hoop, okay, times omega hula hoop. I convert that to frequencies again just by dividing both sides by 2 pi. So the conventional frequency is just the mass of the hula hoop, or hula hoop squared, divided by Sam's moment of inertia, which you're given, and the moment of inertia again of the hula hoop, which we know is just its mass times its radius squared because it's a hoop, times the frequency of the hula hoop. And so we can plug in the numbers now for everything. So that's just frequency of Sam will be equal to 2.0 for the hula hoop's mass, 0.51 squared for its radius squared, divided by Sam's moment of inertia, which you're given, plus 2.0 times 0.51 squared, again for mhrh squared, times the rotational motion, which we're given all the way up here is 2.5 revolutions per second, and the answer is 1.1 revolutions per second. So after everything is done, both Ann and Sam are moving away, directly away from each other, and they're rotating in opposite directions. And that's it.